Hi, everyone. Thank you so much for taking time today to watch my lecture. I'm really grateful to Julie, Jean-Philippe, Ross, and Suzanne for selecting me for this honor. I thank my mentors, collaborators, and friends, including students and postdocs, for helping to shape the ideas I'll describe to you today. I'm hoping to be able to keep you engaged while I give you an overview on the field of research that I'm deeply interested in, that is, the interpretation of the rock record to understand the dynamics of the earthquake cycle, including, but not limited to, the earthquakes themselves. It's a rare opportunity to show a lot of beautiful rocks to a mostly geophysical audience, and I will try to give you a window on how to read the rock record and to make it accessible and interesting. And for those of you who are missing fieldwork as I am, I'll provide a nice slideshow and maybe some inspiration to visit the field again as soon as we can. Earthquakes, of course, are the shaking produced by waves emanating from the rapid slip on a fault. Being transient phenomena, they are mostly studied by seismologists who lay out instruments to record the seismic waveforms and study them to learn about the size of the earthquake, its duration, slip speed, and rupture speed, and the patterns of smaller earthquakes around it. Of course, none of these attributes creates a permanent record in the rocks. They're all elastic. When the seismic waves reach Earth's surface, the tiny details at the source are not really part of the picture. The majority of earthquakes are remarkably similar to one another. Similar stress drop, similar scaling. The details of the process at the source don't seem to make much of a difference. In fact, this amazing compilation by Dittorio and others shows that, regardless of the composition, all rocks weaken to similar low-friction states at seismic slip speeds. This is consistent with earthquakes being seismologically similar regardless of the rocks in which they occur. So why would we want to study the geologic details inside fault zones? The scale of a geologic study, usually microns up to tens of meters or hundreds of meters, is well below the scale of interest for big earthquakes, which are the earthquakes whose details are well resolved in geophysical observations. But the geological scale of observation is ideal for looking at the details of the source processes, the scale of slip, the scale of fracturing, healing, and the local changes in deformation style that impact the strength of faults. The study of exhumed faults to learn about earthquakes is not particularly new, but it remains a small field. Rick Simpson's PhD work in the Outer Hebrides created the modern view of pseudotachylytes as the product of frictional melting during earthquakes, and also explained why melting doesn't always happen. In 1989, another key paper crystallized the notion that earthquakes are part of the long-term deformation patterns that structural geologists study, and that the earthquake cycle can be elucidated through the studies of ancient fault zones. It wasn't much later that Darrell Cowan's 1999 paper, he examined the potential of rock record to be used for understanding earthquakes. He says to the community, hey, let's put some reliable criteria here. Let's relate geophysical observables to a potential for geologic preservation and be rigorous about it. Darrell's conclusion was that the phenomenon that only occurred during earthquakes and not during any other deformation events was frictional heating. He argued that only pseudotachylytes can be confidently identified as ancient earthquakes. Luckily, subsequent work has enabled us to add a few more diagnostic features, so we really can do a lot more with the rock record of ancient seismicity than we could 21 years ago. Pseudotachylytes are the most widely known fossil earthquakes in the rock record. This one is pretty archetypal, a sharp-edged, blackish, fine-grained vein, across which the change in rock fabric shows that displacement has occurred. Pseudotachylytes are much more abundant than most people realize, but they aren't always as clear and obvious as this one, so they mostly get overlooked by field geologists and rarely reported. They also don't last long in most fault cores due to subsequent shear deformation and fluid flow. Oftentimes, damage zones are the best place to see them. Pseudotachylytes have been broadly utilized as archives of earthquake dynamics, and we're learning a lot from them. Here's an example of a study that involved collecting field data with a big group of students. In central Maine, a long, narrow outcrop of myelinite was unearthed when a gravel pit operator reached the bottom of the Pleistocene till. This myelinite strand belongs to the Norumbega shear zone, whose many strands form a braided, long-lived deformation zone of complex history, stretching parallel to the Atlantic coast from New Brunswick at least to Massachusetts. Students from University of Southern Maine and from McGill University spent several days mapping out the outcrop using differential GPS and locating the tiniest features manually. Here's an example of what we found here, intersecting pseudotachylyte veins with mixing and pooling at fault intersections, showing that the networks of fault slip simultaneously during a single earthquake. You can see how easy it would be to overlook these if you weren't specifically interested in them. I'm going to interpret this photo for you. Let's imagine that the wall rock at the top of the photo is held stationary, and look at the slip relative to that. A hairline pseudotachylyte fault vein runs across the center of the photo. Like nearly all the faults in this outcrop, it's dextral. You can see from the curved edge of the outcrop on the left side of the photo that we can properly measure the strike and dip of this fault. It's got a friend, a little splay here. It's dextral as well. It's not conjugate. I know that because of the pull apart created at the top end where it meets the first fault. There's a pool of pseudotachylyte that drained into that pull apart from the two slipping faults and quenched there. Based on the size of the pool, the slip on that splay fault is apparently about 1 centimeter. There are a few more features that formed at the same time. The wedge-shaped block of wall rock between the two faults extended with two Mode 1 or Mode 2 cracks. There's even a little step over in one of them with a pool of melt in it too. And there's a big injection vein there emanating from the splay fault as well. And if you're looking carefully, you might have noticed there's an older pseudotachylyte vein that's a bit harder to see. It juxtaposes a few black smudgy layers here and there that may very well be still older, ductily deformed pseudotachylyte veins. That kind of thing is common in the Norumbega. Using these types of intersection relationships, we were able to map linked networks of pseudotachylyte veins across the myelinite outcrop. The resulting map shows that each earthquake ruptured a set of long parallel faults with smaller faults linking in between or splaying out to possibly extend the rupture network outside of the outcrop, that is, outside of our field of view. Some vein traces appeared on smooth rock surfaces where we couldn't discern their three-dimensional orientation, but wherever possible, we measured the orientation of each vein as it approached a fault intersection. We noted displacement and changes in displacement where possible. We looked at the direction of branching angles at intersections. The displacements on individual fault strands were ranging between 2 to 18 centimeters. So the earthquakes that ruptured through these networks had total displacements in the tens of centimeters. The rupture areas in total were obviously much longer than our 70-meter long outcrop. The networks may be broader too, as connections between the veins are, if anything, under-recognized due to outcrop surface weathering, the tiny size of the veins, and the limitations of the outcrop exposure. A few characteristics of the rupture networks emerged from our analysis. One is a simple geometric constraint. When two faults converge, there's a step change in the displacement from one side of the intersection to the other. The change in displacement is most clearly expressed as the width of the dilation zones. Second, when comparing the orientation of the through-going fault at an intersection, shown on the stereo net with black symbols, to the orientation of the vein which terminates at the intersection, gray symbols, the range of the orientations is about the same. This means the rupture network is essentially anastomosing, and the longest faults are wavy, as in this green rupture network. Lastly, the intersection angles are distributed over a broad range from about 0 to 55 degrees. This is important because in a fault network slipping quasi-statically, it's unlikely that two faults 55 degrees apart would slip at the same time. This confirms that the many individual fault strands in each rupture reflects the dynamic stress conditions triggering slip on otherwise unfavorable faults. So what did we learn about earthquake rupture? Well, if earthquake slip is distributed on multiple fault surfaces through a network, the degree of frictional heating, and therefore probably slip weakening, might be reduced on each surface, limiting the total slip. Abrupt changes in displacement at fault intersections might consume rupture tip energy and emit more high-frequency seismic waves. This could be indicated by dips in the rupture tip velocity. So what we're revealing here could be the geological cause of the seismological complexities that might occur in all earthquakes, even though they're difficult to resolve unless the earthquakes are large. Since Sterrell's 1999 paper, researchers have discovered a lot of other permanent signatures of fault heating. A lot of thermal reactions occur below the melting point of rocks, so this increases the detectability of fossil earthquakes. Besides fast slip, earthquakes can be identified based on an effect of fast dynamic rupture, which is thought to cause a pulse of high stress at the rupture tip. We use fracture patterns that we can relate to very fast stressing rates and high transient stresses associated with this pulse. Many rock-forming minerals react with flash heating to devolatilize, leaving permanent chemical and mechanical damage. This image shows the aftermath of co-seismic decarbonation reactions in a dolomite fault zone: brecciation, dissolution, fluidization. In other fault rocks, temperature spikes can leave signatures such as dewatered clay and gouges. They can cause trace elements to exchange between minerals and fluids, oxidize metallic oxides, and release CO2 from carbonate-hosted faults like this one. The release of volatiles can also contribute to transient pressurization in the faults. And organic biomarker molecules increase in thermal maturity on short timescales. Recent work has calibrated these reactions for a range of biomarker molecules spanning from low to high temperature. This method seems to work in a lot of diverse faults. Here's an example of the specific fracture patterns that have been associated with extreme stresses at the seismic rupture tip. This example shows a laboratory fault in homolite, a transparent plastic, that spawns closely spaced, high-angle arcuate cracks off the fault surface as the rupture tip passes. In the field, we found nearly identical fracture arrays along microbreccia fault cores in an exhumed fault. Though we didn't find pseudotachylyte on this fault, we consider these fracture arrays to be the equivalent evidence of past earthquakes. This is a small-scale example of dynamic fracturing along a small fault, but it's thought that large supershear ruptures can pulverize wide swaths of wall rock around fault zones. So here's another amazing example of a shear zone which preserves a lot of both co-seismic and potentially post-seismic deformation. This is Fort Foster, Maine. This locality is known for Mark Swanson's studies of pseudotachylyte vein geometries. Lately, we've been using these famous pseudotachylites not to study the earthquakes themselves, but to look for off-fault and post-slip deformation patterns. Catherine Ross and Sam Mateer have completed master's projects here, so I'll show you a few things they have found. The pseudotachylites can be hard to see, as they weather the same color as the myelinite, which is mafic in composition. This photo shows an exceptionally large injection vein emanating from a hairline-thin pseudotachylyte fault. Zooming in on the root of the pseudotachylyte injection vein, I hope you can see the source fault. It's so thin, you can just make it out by looking for the sharp discontinuity in the myelinite, here, and the pseudotachylyte that came from it is here. Making injection veins this big requires the wall rock to crack and open. The opening direction on those cracks is approximately parallel to the slip direction on the earthquake slip surface. That had to happen co-seismically because the pseudotachylyte melt quench time is of the same order as the time for slip at a point on the fault, about 1/100th of a second to 1 second. Here's another off-fault injection of pseudotachylyte, but in a different geometry. The seismic fault is here. The wall rock that is above the source fault buckled and shortened when the fault slipped, creating this little box fold. The core of the box fold created a void which filled with pseudotachylyte. That's only possible if the box fold formed during the quench time of the pseudotachylyte, so probably significantly less than 1 second. The fold was formed by the propagation of those little kinks, which is typical fold style in layered media capable of interlayered slip. But folding is generally thought of as a slow ductile process. There are a lot of folds in the wall rock here that must have been co-seismic. Here we have a tiny fold viewed in thin section that involved faulting and buckling of the myelinite foliation. The green layers are amphibole rich, and the clear layers are quartz. The white arrows indicate a pseudotachylyte vein that was caught up in the buckling layers. The pseudotachylyte flowed into the void in the hinge region produced by the outer layers breaking. This means it was still fluid when the fold formed. The fold, again, had to form very quickly. All over the outcrop, we can see another shape of folds. They're intrafolial isoclinal folds in discrete layers between the pseudotachylyte faults. The foliation outside of this fault pair is pretty straight, but inside it is very convoluted. The folds are cut by a number of very short faults, and in fact, they take up some of the bending of the layers around the hinge zones. Injection veins also emanate from the faults and sometimes also from the smaller faults. So some of these small-scale structures are clearly linked to slip on the big faults, but others are not. The relationship to pseudotachylyte tells us that some of this near-fault deformation must be co-seismic. So Catherine mapped the earthquake rupture surfaces using the measured displacements from the field, calculated the Coulomb static stress change that would have been caused by the earthquake. She then mapped the wall rock deformation structures and compared the strain represented by those structures to the predicted static stress changes. So here's a cartoon showing how this all evolves. Prior to any given earthquake, the myelinite zone had a wavy foliation with lots of small local folds, which don't have any faults in the hinges. These are ductile folds in the myelinite that form during the long-term creep in the shear zone. When the earthquake propagated through the myelinite zone, branching locally into subparallel fault strands, it created pseudotachylyte. Locally, the pseudotachylyte filled opening mode cracks in the wall rock. Catherine's analysis shows that these injections preferentially occur in spots along the fault where the static stress change due to earthquake slip would favor the opening mode cracks. So both dynamic stress conditions and the quasi-static stress change cooperate to create injection veins. Large and irregularly shaped pseudotachylyte injections formed that required wall rock to deform to accommodate their size. Subsidiary faults developed. Some crossed over the wall rock between the principal fault strands. These clearly had to develop during the earthquake, as did any small kink that filled with pseudotachylyte. Some faults are short and isolated, usually in small clusters of parallel faults. The offset on those faults were so tiny we could barely measure them in the field at hundreds of microns. There's no direct structural connection between these faults and the co-seismic faults, but they act to create tiny changes in the shape of the wall rock blocks. They probably slipped during or immediately after the earthquake when the rocks experienced the greatest stress magnitudes or stress changes. After the earthquake, afterslip might be accommodated by slow slip-on faults, or it might be accommodated by wall rock creep in the same direction. Some of the wall rock folds have broken quartz layers and bent amphibole layers around their hinges. This suggests that the folds formed slowly enough for some of the minerals to deform ductilely, but fast enough that the quartz could not keep up and was fractured. So what does all this tiny structural mapping actually tell us about earthquakes? Well, for one, some amount of the total displacement during the earthquake, or the afterslip, may not be slip at all. Volumetric strain in the wall rock could be responsible for the displacement, and it could be accommodated by lots of microfaults or by folding, which is a mostly viscous process. The deformation we've shown here occurred at a temperature of about 400 degrees C, which corresponds to the brittle viscous transition in these rocks and would be equivalent to a depth of about 13 kilometers in the San Andreas Fault. Many large earthquakes nucleate in this region near the lower limit of the seismogenic zone. So this combination of on and off fault deformation, while not resolvable geodetically, might actually be important for resetting faults after earthquakes, controlling the post-seismic adjustments in the deep fault zones, and controlling healing and locking. There are clear signatures of aseismic creep as well in the rock record. These have been understood for a long time, but recent advances have helped to refine the methods for interpreting crystalloplastic deformation fabrics. Where quartz is abundant, well-calibrated paleopiezometers can be applied to estimate shear stress during creep. Near the brittle viscous transition, single mineral strain rates are well described by power laws. This quartz myelinite from the Leech River Shear Zone, a hot subduction thrust active at about 550 degrees C and exposed on Vancouver Island, most likely deformed at rates similar to those predicted from quartz flow laws. But the thin selvages of mica which divide the layers, though volumetrically insignificant, might have allowed the shear zone to creep faster, or to creep at a much lower stress than what we would predict from the quartz laws alone. Zooming out, the sheet-like quartz layers are isolated between layers of mica schist, which looks dark gray in this picture because the outcrop spends much of the year underwater. Some quartz layers form boot ends, implying that they were stronger than the schists during creep. In this case, the quartz flow law might significantly overestimate the strength of the shear zone rocks. A closer look at the schist matrix shows the strong shape-preferred alignments of quartz grains and vein fabrics, along with dark mineral concentrations along their edges that suggest that solution creep has been active in these rocks. The rates of rock deformation by solution creep are highly sensitive to mineralogy, the combinations of minerals, which we can observe, but also to transient conditions such as poor fluid chemistry, poor size and shape, and poor connectivity, which continually change and can vary locally during deformation. So these are attributes we can't get out of ancient exhumed faults, which limits the precision at which we can estimate the shear stress and the strain rate in shear zones during creep and healing. The more heterogeneous the rocks get, the more complicated it gets to understand the blend of mechanisms that characterize both fast and slow deformation in plate boundaries. Diving a bit deeper into subduction zones, we get into some really beautiful metamorphic rocks that have structures expressive of significant strength variability, the blue schists and eclogites. This is a blue schist facies rock from Angel Island in the Franciscan Complex in California, a little wedge of chemical sediments that's nestled in between greenish pillow basalts. Blue schists are of particular interest because they correspond in depth temperature space to the plate boundary conditions in cold subduction zones near the base of the seismogenic zone or even deeper. Here's a myelinite zone formed in these low temperature blue schist facies chemical sediments. The dominant minerals here are stilpnomalane, sodic amphibole, and quartz. We think these myelinites formed at temperatures around 300 to 350 degrees C at depths of about 30 kilometers, a cold subduction zone. But since we don't have garnet, the pressure estimate is a minimum based on the presence of jadeite. These myelinites are clearly high-strain rocks, but they don't have much composition in common with continental shear zones. Epidote group minerals, sodic amphiboles, lawsonite, and sodic pyroxenes are the load-bearing minerals. We think aqueous fluids were abundant during the deformation due to dewatering reactions, and fabrics related to solution creep are dominant, which is a fluid-involved diffusive process. So earthquakes sometimes nucleate at these depths, but in many places, these rocks correlate to slow slip, low-frequency earthquakes, and tectonic tremor. The estimated pressure temperature conditions of the Angel Island mylonites correspond well to the source region of seismic tremor and low-frequency earthquakes in subduction zones such as Ryukyu, Key Peninsula, and the Hikurangi Trough, as shown in this compilation by Jamie Kirkpatrick and others. An important insight from Jamie's paper here is that tectonic tremor and low-frequency earthquakes are happening at a lot of pressure temperature conditions. So that indicates that any single temperature-related deformation mechanism isn't likely to provide a general explanation for slow slip phenomena. One way to make slow slips happen is in a zone of mixed materials, usually imagined as blobs of velocity-weakening, strong rock encompassed within a volume of velocity-strengthening, weak rock. Here's a conceptual cartoon of this from Chesler and Krieger, and two possible geologic examples. The top photo shows a beautiful red and green boudin of eclogite from Kotowski and Baer, which is very hard and brittle as evidenced by white quartz-filled fractures. The boudin is embedded in a matrix of glaucophane schist, which flowed at about 400 to 500 degrees C by dislocation creep, which produced power law viscous rheology. The lower photo is from Falgering and Den Hartog and shows sandstone boudins in shale matrix at deformation temperatures around 300 C. The flow in these lower grade metasediments is controlled not by crystal plasticity, but by solution creep. So these models based on material heterogeneity seem to reproduce the right behaviors and imply a relationship between the scale of geologic heterogeneity and the scale of fast slip patches. We know that the subduction zone melanges have a block and matrix structure that seems compatible with this. Here's an example from Ring Mountain, a big old block of mafic blue schist embedded in a sea of serpentinite. This is one of many 10-meter scale blocks in this melange, but at least at this site, which has been described by previous researchers as a paleo-subduction interface, they don't get bigger than about 10 to 15 meters. Some melanges do contain blocks up to bigger scales, big enough to represent slip patches that would produce a detectable seismic signal. Falgering and Den Hartog suggested that even seamounts or similar seafloor topography might be the blocks that cause the seismic slip within a slow slip event. But what if the relationship between material heterogeneities and slip events isn't quite so literal? Here's a cross-section of the Livingstone Fault in New Zealand from Tarling and others. In their model, the blocks are fluid sources, and the increasing pore pressure is responsible for local embrittlement around the blocks. This idea decouples the exact block location and size from the slip patch, because, of course, the fluids can migrate and coalesce into larger pore pressure patches within the viscous matrix. There are other ways that blocks of contrasting rocks in a flow matrix could contribute to mixed mode behavior to produce slow slip and tremor. This is Noah Phillips's map of the Mugi Melange. Noah mapped these metabasalt blocks in the melange, which contain a mineral assemblage of chlorite and albite, a pretty simple rock, really, and a very representative of the subducting oceanic crust in the seismogenic zone. The metabasalt is velocity weakening, and the surrounding shale matrix is velocity strengthening. Here's a photo of one of these blocks. The grayish green in the middle is the metabasalt, and the dark gray streaky rock surrounding it is the foliated shale matrix. Since the chlorite plus albite rock is soft and ground up, it gets drawn out along slip surfaces in the melange during matrix flow. It creates bridges of velocity-weakening material from block to block. This creates a slip surface where slip could localize, accelerate, and maybe go dynamic. These bridges probably don't last very long because the shale matrix flowing around them would deform and distort them. Now, the slip patch size, that is the size of the velocity-weakening patch, is then decoupled from the exact size of the blocks in the melange. It's possible by this mechanism to produce much bigger patches for slow slip, which seems like the right way to get to a situation where the whole subduction interface might have the potential to produce tremor. There are other, tinier mechanisms that might come into play to produce slip and tremor. Sam Carruthers collected a garnet-bearing blue schist with a mineral assemblage and a matrix fabric consistent with conditions of about 350 to 500 degrees C and about 1 to 1.5 GPa. This corresponds to a depth of 30 to 40 kilometers in a cold subduction zone. With Greg Hurst's group at Brown, we deformed these blue schist at temperature and confining pressure conditions equivalent to where the rock actually exists in the earth. The natural fabrics play a big role in controlling the deformation that occurred. This image is of a tiny 6 millimeter long core sample of the garnet blue schist, which has been shortened in the horizontal direction of the photo at a temperature of 450 C. The core was cut so that the foliation in the rock is at 45 degrees to the axial stress direction. There are two main features that formed during the experiment that I want to show you: a kink band at the high angle to the foliation, shown in red, and a tiny fault and damage zone, shown in blue. Now we'll zoom in on those. Red one first. So here's the kink band that formed in an orientation at a very high angle to the natural foliation. The clear minerals with high relief are zoisite, and the blue low relief crystals are glaucophane. This kink band is formed by the high-density array of tiny fractures that cut the zoisite crystals. Strangely, the fractures do not seem to cut across the glaucophane crystals, which apparently bent through the kink without much protest. This little kink contributed a millimeter or so of shortening to the sample through a mixture of fracturing in the brittle grains and apparently flow in the plastic ones. And here's the localized shear band that formed parallel to the natural foliation. And in this kink band, the brittlest minerals were fractured as well. These garnets just exploded into tiny dust, and then distributed shear in the shear band stretched out their fragments into these beautiful tails. The tails look brown in this plain light image, but they are just garnet, with particles so fine that you can't see them, as shown by this backscattered electron image. What was unique about these experiments was that even though there were audible acoustic emissions, there was no stress drop at all during the experiment. So all this fracturing went on without ever linking up together. This top plot shows the differential stress during the experiment, and the middle and lower plots show the acoustic emissions. Even with the formation of through-going shear fractures and kinks and some very loud fracturing events inside the sample, the smooth shear stress curve in the top plot shows that the viscous processes dominated the macroscopic deformation, and the brittle deformation was isolated to these small features. These experimental samples are tiny, and the garnets in the blue schist certainly don't scale up to the 100 or 1,000 meter slip patches equivalent to, say, a Cascadia-style tremor and slip event. But the chaining together of many garnets, triggered by localized viscous slipping zone cutting through them, could produce a lot of noise, and the stringing out of the garnet dust into tails in the adjacent shear band, which look black here in this cross-polarized light photomicrograph, show that the macroscopic displacement is linked to, but not exactly correlated to, the sites of fracturing. Maybe this relationship is analogous to deep tremor and slip. So it's clear that there are myriad ways that brittle and ductile rocks could deform together, both within the seismogenic zone and deeper down in the interesting regions of slow earthquakes, silent slip, and tremor. Those phenomena probably reflect a host of different deformation mechanisms in different settings. Some of these deformation mechanisms are well described by existing theory and rheological laws, and others are not. Until we isolate the exact processes responsible for these deformation transients, we won't be in a good position to relate them to the questions of broader interest, such as how deep slow slip contributes to loading locked seismogenic zones. So although I'm enjoying showing you some of my loveliest rocks, I have to say that the structures and these combinations of structures that I'm showing you are typical, they're average, they're very common if you get the right rocks from the right tectonic setting and conditions. When I first heard about tremor and slip, I thought, oh wow, the evidence for this kind of behavior has been known for a long time, because structural geologists have been looking at zones of mixed brittle and ductile structures for a long time. So there we are, and the present challenge is to be able to link these observations and exhumed rocks to active settings, to quantify things, to develop mechanistic understandings of phenomena that could be built into predictive models. But we haven't leveraged the powers of geological observation as far as they can go. We have this incredible record of fault processes, which has the potential to really reveal important insights. For example, which deformation mechanisms control slip initiation or facilitate healing and locking, and how slip jumps around in a fault zone over time. But we only have a few tools for reading the record. There's a lot of the geologic record that we can't interpret yet. So there's a lot of work to be done. There is still so much unknown that traditional field and petrographic techniques are still turning up a lot of new insights. The more fault behaviors that are observed in active plate boundaries, the more motivated we should be as geologists to go to the field and try to understand what we're seeing. And then, this is an important thing to point out, in addition to the few attributes of fault rocks that we can interpret, that we know how they formed, there are all kinds of features and complexities that we cannot yet understand. Here's an example of a quartz mirror surface on the Corona Heights Fault in San Francisco. The coating of clear iridescent opal and silica is a millimeter or two thick all over this grooved fault surface. The shallow fault cuts radiolarian cherts, which are 99% quartz. There's no hydrothermal veins nearby, and it's as close as possible to a simple fault that could be replicated in the lab. There's one mineral involved, stress is low, no pore pressure. Many workers have argued that fault mirrors form during seismic slip, although the mechanism needs to be assessed independently for every rock type and setting. Using transmission electron microscopy, you can see that the mirror surface is made of tiny, tiny blobs of quartz, which contain inside them even teenier, tinier little rounded blobs of quartz and a few other oxide minerals. The crystals are free of strain and damage. We replicated this very simple case in a lab, shearing chert at a range of velocities, and made a thin coating of particulate amorphous silica with quartz chips in it that effectively lubricated the shearing surface. The same coating formed at slower and faster slip rates, although a thicker coating formed at faster slip rates for the same amount of slip. Dramatic slip weakening occurred in these experiments, so we know that this amorphous nanopowder is very weak at fast slip rates. The similarity in form and size of the particles in our lab-made wear material to the tiny quartz crystals making up the mirror surface of the Corona Heights fault convinced us that we had replicated the natural material. Amorphous silica is metastable, and these particles had high internal strain. So that means that over geologic time, they would recrystallize and form strain-free quartz, and that would happen rather quickly. Okay, in this slide, I've resized all the photomicrographs so they're the same scale, and I've added an image of a similar coating on the famous Dixie Valley fault mirror. It's probably a few thousand years old, so it looks more cohesive and crystallized than our fresh wear material that we made in the lab. Dixie Valley has a screaming active geothermal system, venting high silica waters up the faults, which precipitate opaline veins and cements. It also broke in a series of magnitude 6 and 7 earthquakes in 1954. As of right now, I don't know how to tell in Dixie Valley whether the mirror coating formed due to the hydrothermal precipitation, or totally due to earthquake slip, or maybe the hydrothermal silica gels helped to lubricate the fault and promoted earthquake slip. So every type of fault mirror has to be independently understood in terms of the mineral behaviors and how it forms. There's a lot of recent progress, but still a lot more to learn. Another phenomenon we don't understand very well is delocalization. We know that when slip accelerates, that localization is favored in velocity weakening materials. There are a lot of faults that have very thick layers of granular material that seem coherent. That is, they look like the thick layer sheared together in one event. This is the Nowcliff Thrust in central Namibia. The big orange layers you see are dolomite cataclysite and 2 or 3 anastomosing fault strands, which envelop layers of gray limestone wall rock. This nearly 1 meter thick fault strand has a discrete slip zone at its base and one running through the center, dividing the fault core into 2 half-meter thick units. I'm going to zoom in on the blue arrow. The slipping zone has a sharp base and is composed of microcrystalline carbonate, which is the product of coseismic decarbonation. The number and size of grains increases gradually upward into a grain-supported layer in which large classes of wall rock are distributed. Importantly, this is a gradational boundary, and the slip zone does not cross-cut the thick granular layer, nor vice versa. Within the granular layer, there are flow banding features, defined by grain-size sorted layers and preferential cementation, that indicate the whole layer was fluidized together. This layer is indivisible. These flow folds indicate laminar flow and sorting went on in this thick, deforming granular fault core. So this is a lucky example. Seismic slip must have localized right at the base of the layer, achieved frictional heating temperatures sufficient to decarbonate the fault rock at 850 degrees. Then, according to my interpretation, the resultant pressurization mobilized this unconsolidated granular fault rock. As the gas escaped, the fault locked up again abruptly, preserving these features. The granular layer clearly preserves these flow textures, but if it wasn't in gradational contact with the slipping zone that contains the evidence of thermal decarbonation, it would be ambiguous whether an earthquake had caused the fluidization. This isn't unique to rocks that can produce a lot of fluid either. Here's an example from the Pasagshak Point Thrust, an ancient subduction zone exposed on Kodiak Island, Alaska. You would be forgiven for mistaking this fault rock for a pebbly mudstone like a landslide deposit. But the black clasts and stringers here are pseudotachylyte, which both crosscuts and is deformed within this granular fault rock, which forms a thick composite layer representing unknown numbers of slip events. Again, this large-scale fluidization of granular fault rock occurred in a slipping fault, and fluidized granular materials are defined by a loss of shear resistance. If it wasn't driven by earthquake slip, it probably caused an earthquake. That's my firmly held opinion. But we don't have a good framework for understanding the relationships between shear resistance and granular flow, or the ways in which granular materials can rapidly change behavior, and how this might affect dynamic fault slip. Fast slip in a thick, weak layer might never localize down to the centimeter or millimeter slip zones that are thin enough to see temperature rise and trigger the more well-known weakening mechanisms. But fluidization could be a fault weakening mechanism that doesn't rely on temperature change. Rocks like these previously fluidized layers in the Nalcliffe thrust and the Pisagshak point thrust don't really have a name to distinguish them from other fault gouges or cataclasites. In fact, we're desperately short on terminology for rocks from brittle faults. This is Rick Simpson's proposed classification from 1977. It's basically still in use, with the addition of foliated cataclasites by Chester et al. In 1985. It's a good first pass, but it doesn't name or include a lot of fault rock attributes that are really useful in understanding what deformation processes might have been active in a fault. It relies on cohesion, which in granular fault rocks can be totally independent of slip. For example, fault rocks can increase or decrease cohesion by later cementation or weathering. Randy Williams and I are developing a more rigorous way of naming fault rocks in hopes that a more detailed and focused descriptive framework will really open the door to understanding what these fabrics say about fault rock deformation and ultimately strength and healing mechanisms. So one of the big issues is that we don't have a way to distinguish between different types of foliation. Here are 3 thin sections belonging to Carly Studnicki from shallow cores through the active main strand of the San Andreas Fault near the Elizabeth Tunnel, which brings water through the fault zone into Los Angeles. This segment ruptured to the surface in 1857, and this observed surface displacement was about 4 meters. Each image is 27 millimeters across, a standard thin section. The mineral components of these fault rocks are similar to one another, and the grain size ranges are similar. The big difference between them is the diversity of fabrics. In the left image, the particles are rounded and poorly sorted with a streaky matrix, which is cross-cut by sharp bands of different class size distribution and different class matrix ratios. In my opinion, this tells a story about distributed granular flow, later cross-cut by more discrete slip zones where more intense grain size reduction occurred. That sample showed a broad range of grain sizes, but the middle sample is a mixture of 2 distinct fault rocks. The clasts are locally quite uniform in size and very angular. The pattern of finer and coarser grained areas looks like a mixing of 2 different fluids. This impression is reinforced by the dark films along the borders that divide the 2 grain sizes. This pattern speaks of fluidization of 2 different fault rocks and mixing during slip. On the right, there are 2 zones of well-defined sharp fabrics. The upper right is very fine-grained cemented gouge with bands of insoluble oxides. This is cross-cut by a greenish slip zone with internal gradation and color banding, showing off a lot of small shears and structural complexity. The dark band in the lower left corner is exceptionally fine-grained and speaks of localized, potentially seismic slip. Unfortunately, under existing naming schemes, these are all gouge. The fabrics you see that distinguish these samples, that I would interpret to record the different styles of deformation, have no commonly accepted names or simple descriptors. This lack of language to describe these rocks limits our ability to communicate the diverse range of fault rock features that we need to be able to discuss, compare, and understand, especially between experimentalists and field observationalists, so that we can apply insights from well-controlled laboratory conditions to natural faults. Okay, so I've shown you a gallery of different fault rocks and probably pointed out a few too many times that there was a lot we still don't understand, but that it's exciting to know that fault rock studies might continue revealing insights into earthquake processes. I hope I've made the case that it's just as important to identify seismic fault rocks as to look carefully at the rest of the fault rock fabrics as well, and to understand the relationship between the discrete faults that rupture in earthquakes, the possibility of distributed slip in thicker layers during earthquakes or other slip events, and to look at overprinting features that indicate fault creep and healing. Here's the exhumed Pufadder shear zone in South Africa where it crosses the Orange River. The fault core here is a 15 to 20 meter wide ultramyelinite zone containing countless pseudotachylytes. This is surrounded by a region of intense parallel foliation almost 50 kilometers wide. I think of this as an earthquake highway. When walking along strike, it is easy to see what happened when this shear zone was active. Drag along the shear zone has pulled in many rock types from the surrounding units and drawn them thin like taffy. The paths of earthquake ruptures are preserved as pseudotachylytes and can be traced for tens of meters between the myelinite layers. Intensely fractured breccia horizons also record the passage of earthquake ruptures. Why did some cause dynamic fracturing and others cause melting? We aren't sure. Why are pseudotachylites preferentially concentrated along certain rock types amongst all the thin and heterogeneous layers? Maybe it's their stiffness or their heat capacity, or maybe it's due to the geometric roughness that forms during interseismic flow and boudinage. Older pseudotachylites and dynamic breccias are ductily deformed, recording distributed creep in the myelonites in the interseismic periods. Thick packages of myelonites containing fossil earthquakes buckle and fold during regional shearing, creating geometric strong parts within the shear zone core and helping to localize future slip events. Every stage of the earthquake cycle that we can resolve from the surface, precursory slip, seismic slip, post-seismic creep, locking, even transient slip events, these exhumed faults and shear zones contain a record of every stage that permanent strain occurs and can display the very small strain events that aren't geophysically resolvable but might affect strength and loading. It's my hope and ambition that approaching faults and shear zones as systems will support future development of mechanistic understanding of the earthquake cycle, with ramifications for seismic hazard and for fundamental geodynamics. That requires that we continue the process of observation and discovery, develop new tools, and piece together previously unknown details of rock deformation at all depths in the crust and down into the upper mantle. It requires communication across a variety of disciplines and specialties, and exceptional coordination between field geologists, geochemists, geophysicists, experimentalists, and numerical modelers, which is sometimes difficult, but often rewarding. For field geologists, it's a call to revisit classic localities and paradigms with an earthquake eye, and to carry on with fundamental mapping and exploration so that we can discover more and varied exhumed faults and shear zones to better capture the complexity and the variety of Earth's deformation structures. And with that, I thank you again for your time and attention. I look forward to your questions and comments, and many thanks to the Tectonophysics leadership for this honor, and to AGU for persevering and offering us all a fall meeting experience for 2020. Thanks.